Hello and welcome to today's lesson on the motor effect, which is part of the magnetism and electromagnetism topic in GCSE Separate Science Physics. So in today's lesson we're going to look at understanding what the motor effect is. So if we've been successful and learnt in today's lesson, we should be able to describe the principles of electromagnetism, link the properties of magnets to electromagnetism, describe the effects of the motor effect and explain the motor effect. Now if we are going to look at this in today's lesson, we'll be looking at 4.7.2.2 Fleming's left-hand rule and 4.7.2.3 electric motors in the AQA GCSE Physics Separate Science specification. Now Ørsted had previously discovered the concept of electromagnetism, but he couldn't explain it and he couldn't manipulate it. Michael Faraday later came along and he built the world's first DC motor with the principles of electromagnetism. Now a motor transfers electrical energy into the kinetic energy. So the electrical energy store is turned into the kinetic energy store when work is done. But remember, energy cannot be created, it cannot be destroyed, it can only be transferred. Now we're assuming in this instance that the motor is 100% efficient, which would be a closed system. Now in reality, motors are open systems and there's always some unwanted energy transfer. So when the electrical energy store turns into the kinetic energy store, some of the energy is transferred to the internal energy of the surroundings. Now if we place a potential difference in a metal, we can create a current in this particular wire. Now at this point all the charged particles are aligned in the same direction, so this produces a magnetic field around the wire due to the current being present. Now the direction of the magnetic field is given by the right hand rule, and the magnetic field is always at right angles to the electrical current. Now electromagnets, unlike permanent magnets, can change the size and the direction of its magnetic field. So for example, we can increase the magnetic field strength of an electromagnet by increasing the current through the wire, or we can change the direction of the magnetic field by changing the direction of current flow in our wire. Now there are four basic principles of electromagnetism. When electrical current flows in a wire, a magnetic field is formed around the wire. The stronger the current, the stronger the magnetic field will be. When a current stops flowing, there will be no magnetic field, and when the direction of current is reversed, the magnetic poles reverse. Now we can use these four basic principles to explain how a DC motor works. So to construct a motor, you need two primary pieces of equipment. You need an electromagnet, normally made out of a piece of electrical wire, which when a current passes through the wire, it produces a magnetic field, and when the stronger the current flowing through the wire, the stronger the magnetic field, and when there's no current flowing through the wire, there's no magnetic field produced. We can change the direction of the current flow through the electromagnet, and this changes the direction of the magnetic field the electromagnet produces. Now electromagnets tend to be made out of thin light pieces of wire such as copper. Now the second piece of equipment you will need for a motor is a permanent magnet. Now this is a material which has a constant magnetic field. It can never change its magnetic field strength. So this magnet can never change its north and south pole position. Now permanent magnets tend to be made out of heavy dense materials, and this makes them difficult to move. Now in this example, a horseshoe magnet can be produced, which is a type of permanent magnet with two bar magnets and a metal chassis. Now like a bar magnet, the magnetic field lines in this permanent magnet flow from north pole to south pole. Now we say that in this horseshoe magnet that the magnetic field is uniform because the lines are parallel. Now interestingly, when a conductor cuts through magnetic field lines, it produces a potential difference in the conductor. Now, we can place our electromagnet inside the magnetic field of a permanent magnet. As the electromagnet and permanent magnet are both magnets, their magnetic fields interact with each other, the opposite poles will attract and the like poles will repel. So in this instance, the north pole and north pole of the permanent magnet and electromagnet will repel each other, and the south pole and the south pole of the permanent and electromagnets will repel each other. Now that's a very important idea. So the force is only experienced experienced by the part of the electromagnet which is perpendicular to the permanent magnet. Now the parts which are parallel to the permanent magnet do not experience a force, which we'll consider in the next lesson. So what we can say at this point is the magnetic fields interact to create a pair of forces. Now you'll notice that they'll be acting in the opposite direction. So because we've got one force acting in one direction and another force acting in another direction, the magnetic fields interact to cause the coil to rotate. Now as we know previously, a force which causes rotational motion can be linked into moments, so we can say that the two forces produce moments which cause the coils to rotate. Now the electromagnet will move and rotate to ensure that the opposite poles are facing each other, because the opposite poles attract each other. So the south pole of the electromagnet will want to be next to the north pole of the permanent magnet and vice versa. Now this idea is called the motor effect, because we produce movement, rotation from the electromagnetic attraction and repulsion. Now the permanent magnet should also move as well as the electromagnet, but it only moves a little bit because it's a lot heavier and has a lot more mass compared to the electromagnet. So this causes the opposite poles of the electromagnet and the permanent magnet to line up, and we get motion in our magnets. So as a result, we've got the motor effect. So when a current carrying wire is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other, and the resultant force causes an acceleration of our coil and allows it to rotate. Now the motor works by the attraction and repulsion of magnetic poles. So this means that the motor would only reach half a rotation and stop, because eventually the north and south poles of our permanent and electromagnet would align and attract, so no longer move. So in this particular situation, neither side of the electromagnet would want to move, as it's attracted to either side of the permanent magnet. So Michael Faraday thought about this, and he compensated for this by adding a device into our motor called a split ringed commutator. Now this device flips the magnetic field of the electromagnet by changing the current as it reaches half a rotation. Remember, this is a basic principle of electromagnetism. If we change the direction of the current flow, we change the direction of the magnetic field in the electromagnet. So the split ringed commutator must change the current flow direction every half a rotation to ensure the poles of the two magnets are always in repulsion to each other. Now if the commutator was not found in the motor could only rotate for half a rotation. So the two halves of the rotating commutator swap from one brush to the other, so the commutator reverses the current, keeping the forces in the same direction, the same repulsive force. So this allows the coil to complete a full rotation. So Faraday compensated by adding a split ring commutator into our motor. This changes the direction of current flow, allowing the magnet to complete a full rotation, and this change of direction of current flow happens every half a rotation. Now a split ring commutator is made out of graphite. Now that's because graphite is an electrical conductor, and in addition to that it's very slippery because there's very weak intermolecular forces of attraction between the different layers of graphite. So it causes very little friction when in contact with the rotating commutator, so therefore there's less energy dissipated to the internal energy store of the surrounding. So this leads us to the idea of a DC motor. The direct current motor is the motor used throughout the world today. So you can see with this idea of a current carrying wire, a permanent magnet and a commutator, you can get this rotational motion, and it's very important you can understand how this effect works. So an electromagnet is placed inside the magnetic field of a permanent magnet. The sides of the coil parallel to the magnet experience a force in opposite directions, and the forces cause moments that act in the same direction. Now these moments cause the coil to rotate, and this is a motor. Now each half revolution, the two halves of the rotating commutator swap from one brush to the other brush, so the commutator reverses the current in the coil, keeping the forces in the same direction, and the coil keeps on rotating. Now, in our previous example, we've considered the electromagnet in a motor to be a wire. However, in the real world, many electromagnets are actually coils of wire. This is because our coiled wire gives a stronger magnetic force, so as a result it allows it to rotate faster. So this is a schematic from looking over the top of the motor. So you can see we've got a north pole and a south pole from our permanent magnet, and we've got a coil in between that, and we've got the current moving in one direction in section 1 and in the other direction in section 2. Now we place a split ringed commutator here to help us with our motor rotate, and we've got our permanent magnet there and our electromagnet in the middle. Now, as the current is moving around the coil in different directions, we can split the coil up into two sections, section 1 and section 2. Now, we don't have to consider the top section and the bottom section of the coil, as they're parallel to the field lines of the permanent magnet, so experience no attraction and repulsion. Now, we only consider section 1 and section 2 as labelled in our diagram because they're perpendicular to the magnetic field of the permanent magnet. Now, in each section, the current is moving in a different way, so the magnetic fields they produce are in opposite directions. This means the two sections, the sides of the coil, experience the same interaction, repulsion, as they're next to the different poles of the permanent magnet, and this allows our coil of wire to rotate. Now, it can be easy to visualize the repulsion or attraction experienced by an electromagnet and a permanent magnet as a force between the two. Now, it's appropriate because a resultant force will cause this electromagnet, this coil of wire, to accelerate. Now, section 1 and section 2 of our electromagnet experience a magnetic force in opposite directions, giving a resultant force. Now, remember, the force due to the magnetic interaction between the permanent magnet and the electromagnet are non-contact forces. So this magnetic force produced causes the electromagnet to spin. Now, the larger the magnetic force, the faster the motor will spin. Now, our magnetic force can be increased by increasing the current through the electromagnet, increasing the magnetic field strength of the permanent magnet, or increasing the length of the current carrying wire in the field. So when a conductor carrying a current is placed in the magnetic field, the magnet producing the field and the conductor exert a non-contact magnetic force on each other. This resultant force causes the acceleration of the motor. Now, when we're considering the forces, the coil spins as there's a force due to the motor effect on each side of the coil, and these forces act in opposite directions. Now, there's no force when the two magnets are parallel with each other, but there's the greatest force when the two magnets are perpendicular to each other. So we can represent this idea of the magnetic force, the magnetic field, and the current with the following a particular picture. Now, the magnetic force and the current being perpendicular to each other is a key idea of electromagnetism, and so is the idea that the magnetic force and the magnetic field are perpendicular to each other as well. Now, what we can do is we can use a trick in physics to work out what the direction of our magnetic force is going to be acting on our electromagnet. So this is called Fleming's left-hand rule. So Fleming's left-hand rule shows the direction of movement on a conductor, or the direction of the magnetic force due to a current carrying wire being placed inside of a magnetic field. So what you would do to work this out is with your left hand you would stick your thumbs up. Now, the thumb shows the direction of the magnetic force and therefore the direction of movement of the wire. Your first finger you should point outwards with. Now, your first finger shows the direction of the magnetic field, and with the same hand, with your left hand, you should then swear with your middle finger. Now, the second finger shows the direction of the current. Now, we can use this trick to work out either the direction of the magnetic force, the direction of the magnetic field, or the direction of the current flow with your left hand as shown. So let's just go over this key idea again. Fleming's left-hand rule shows the direction of movement on a conductor carrying a current in a magnetic field. This allows you to work out the direction of the magnetic force, and the magnetic force causes the movement of our coil, of our conductor, of our electromagnet. So the first finger represents the direction of the magnetic field from north to south. The second finger represents the direction of current flow. Now remember, it's from positive to negative, it's not the direction of electron flow, and the thumb represents the direction of thrust, or the direction of resultant motion. It is the direction direction of our magnetic force. So in a question, how should you use this? Well, step one, you place the knuckle of your first finger at the north pole of your permanent magnet and point your finger to the south pole of the permanent magnet. Then you place the second finger pointing in the direction of the current flow, and you may have to reorientate your first finger to ensure that step one and step two is satisfied simultaneously. At that point, the direction your thumb points in is the direction of the magnetic force and therefore the direction of movement of the wire. So what have we looked at in today's lesson? When a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. This is called the motor effect, and you should be able to show that with Fleming's left-hand rule you can represent the relative orientations of the force, the current and the conductor, so the magnetic field of the conductor in that particular situation. Now you should also be aware of the different factors that affect the size of the force on a conductor, and you should also be aware that a coil of wire carrying a current in a magnetic field tends to rotate, and this is the basis of an electrical motor, and you should be able to explain how the force on a conductor in a magnetic field causes the rotation of coil in an electrical motor. So if we've been successful and learnt in today's lesson, we should be able to describe the principles of electromagnetism, link the properties of electromagnets to electromagnetism, describe the effects of the motor effect and explain the motor effect. I hope you've enjoyed today's lesson on the motor effect, which is part of the magnetism and electromagnetism topic in GCSE Separate Science Physics. Thank you very much for listening and have a lovely day.